Okay. All right. So now we're going to look mostly at the physiology of the eye today. We talked more about the structures last time, so now we'll talk about how all those structures work. Okay, so a little bit more details on the rods and the cones here. So the rods are our light receptors in our eye that work for dim light, and they're for our peripheral vision, right? So things that we're seeing kind of on the outside of our retinas, not right there in the middle in the fovea centralis, but the things in our peripheral vision. Not the thing we're focusing on, but kind of everything else. Okay. We got way more of these than we do cones. Okay. And we don't really find them much in that fovea centralis area. Okay. They're much more sensitive to light, which means they get stimulated with lower light. That's why they're good for dim light situations. Okay. And they don't detect color. They're very low resolution. We'll talk about kind of the implications of that, but picture the images you get from your rods as being like a very grainy photo, or like when you zoom in really close on a digital photo, it's kind of all grainy and you can't really see clearly what it is. That's kind of the type of image we get from our rods. Okay. When we look at our cones, the function of these is they're specialized to detect color. Okay, we've got three types: blue, red, and green. Okay, so it's really just a combo of these three colors that gives us all the colors in the whole spectrum that we can see, right? One combo or another. Okay, so these are not as sensitive. It takes a lot more light, a lot brighter light to stimulate these. And we have a lot less of them because most of them are there in the fovea centralis, but they're kind of all clumped right there in that spot that we're trying to focus the light on. Okay, so these give us a much more high resolution image, and we'll talk about why we have that difference in resolution from the two. Okay, so we'll talk about that next. So when we look at our retina here, we've got this. Um, Take just a quick look and just chat about it with your team briefly. What do you see that's different about the way that the rods are wired to the bipolar cells and the ganglion cells versus the way that the cones are? Okay, go ahead. Chat with each other about it real quick. Yeah, it looked really good. And look good. I wanted to go.
The craziest weekend.
Yeah.
I cannot.
Yeah, I served Monday. That was like it hadn't started really yet, but it's a little bit. But I have like a mid-length 7.4. Yeah, yeah. So me and my son we went to OB. Me and my son did, but yeah, it was like just starting to pick up that day. But yeah, yeah.
Do you get it? Is it hard to fit it in usually with the?
Yeah, totally. Yeah, for sure. Yeah. All right. So what do you guys see? What's the difference? How are they wired different? Yeah.
Cones have more branches.
Cones have more branches. Okay. So we're seeing, you're talking about like, yeah, the kind of like three branches there. We kind of got that singular connection there. Okay. What else? Yeah. Just one to one. Yeah. Yeah. And that's the big difference in resolution is this here, where we've got three rods connecting to one bipolar cell, which then connects to one ganglion cell, right? Really, in actuality, it's much, much more extreme than that. It might be on the level of 100 rods connecting to one bipolar cell because there's only, like it says, there are only 1 million ganglion cells for the 105 million photoreceptors, right? So that means we might have 100 of these rods connecting all to the same ganglion cell, okay? So if we've got this whole region with our 100 rods in it, all of that's connected to the ganglion, to one ganglion cell. The brain doesn't know whether the light hit right here, or it hit right here, or it hit right here, right? Because it just activates that ganglion cell, and then we get an action potential up to the brain. The brain just knows it got a signal from that one, right? It doesn't know where in this whole region it was activated, right? So that So that makes it kind of blurry, right? Your brain has to kind of fill in the gaps on where it doesn't know exactly what it looks like, right? But with a cone, it's a 1-to-1 or maybe 1-to-3 situation. So if we're only covering like this much ground, then the brain knows with that level of certainty where the light came from, right? And it can piece together a clear image with a higher resolution. So that's really the deal with the resolution. Is kind of the way that they're wired like that. Yeah, Ethan. Fovea centralis, yeah.
Spot in the center partition, or it will be like focused differently so that
Yeah, we've got some. We have some rods there, not a lot, but it's mostly cones. So yeah, you can definitely still use the rods in that fovea centralis. But yeah, you're still trying to focus the light there. But yeah, but the cones, if it's pretty dark, aren't even really being used much at all. Yeah. hmm Yeah. Yeah, so a little bit more on this. So when we look at those rods and cones, we have these two different structures called rhodopsin and iodopsin. Okay, so these are the pigments found in the outer segment of our rods and cones. The rods have the rhodopsin one, and the cones have the iodopsin one. Okay, the components of this includes retinol in both of them. Okay, and then a different membrane protein. Okay, so retinol is this little organic molecule that requires vitamin A to make it. Okay, so when we look at foods that are really colorful, typically vegetables are really colorful, got a lot of vitamin A. It's like the idea with like at least when I was a kid, it was like there'd be like in cartoons of bunnies could like see in the dark because they were eating so many carrots. I don't know if that's still in cartoons these days, but the more of those vegetables you eat, it's supposed to be better for your eyes, right? It's all about the vitamin A. Okay. Um, so that's the retinal part. And then the opsin part is this big membrane protein that we see in the rods. And that's what the retinal is bound to. And we'll talk about that and why those two things are important in a second. But it's really the detaching of the retinal that activates the rods, and then that is what sends a signal down the cells. Okay, so the cones are just slightly different. They've still got the retinal, but they have photopsin instead of opsin. And this is the one that's unique in the three different colors, right? So there's the red, the blue, and the green of these photopsin proteins. And so a cone is going to have one of those three types. And so again, it's just all the combos of these different colors, right? So red and green together might make something like yellow, more red than green, maybe more orange, right? If we stimulate all of our cones at once, we see white. Yeah, go ahead, Matthew. I was just in case I wanted to do a clicker question on the little color combos, and I didn't want to. Okay, good question. All right. So the rods and cones here, we can see a little bit more closely if we zoom in on one of these rods. We see that it's made of a bunch of these discs kind of stacked on top of each other. And then if we zoom in on one of the kind of membrane part of those discs, then we got this right here. Okay, so we've got the opsin uh, protein and the retinal little molecule as well that's made from vitamin A. And so with retinal, there's two different types. There's cis retinal and there's trans retinal. We can only see the cis retinal here, but the cis one is the one that has the curve in it. It's bent like this, and then trans is going to be straight. And the trans one is the one that's going to fall off of the membrane protein, whereas the cis retinal is bound to the protein tightly. Okay, just real quick, the color of light is all dependent on the frequency of the waves. All right, so the light waves um, uh, change frequency, right? So the lower frequency waves are kind of these darker colors like blue down here, higher frequency out here, more towards the red colors there. You don't need to know more detail than that. Okay, so how does it work? How does rhodopsin respond to light? Okay, so we've got the retinol, we've got the opsin, and the photopsin. All of these are sensitive to light, and they all absorb light, so they're all pigments in a way. Okay, and again, when the retinol absorbs light, it changes from that cis form to the trans form. So pretty much it drives a chemical reaction that straightens out that tail of that chemical. Okay. And when that happens, it falls off of the membrane protein that's bound to either opsin or photopsin. And this is known as bleaching of of the photoreceptors. Okay, and so the retinal can then, by an energy dependent process, can be turned back into the cis form and then put back on the membrane protein. Um, and then it can come off again with some more light that hits it. And each new time it comes off, that sends kind of a new signal to the brain, so we can kind of keep refreshing the image that the brain sees. Okay, so the process looks like this. Again, we're zooming right in on one of those rod areas there. And we can see one of those membrane-bound proteins. This is in the dark here on top, right? So we got the cis version there. You can see that in the dark, sodium is actually rushing into the rod. Kind of feels like it'd be the opposite, right? Like that activation would allow sodium to come in, but it's the opposite. Sodium's always coming in the dark. And then when we activate it, we turn it into transretinal. That comes off. That you don't need to know, you don't need to memorize these steps, but that starts a chain of events that eventually stops sodium from coming into the cell. Okay, and we won't go into much all the molecular details there, but that's kind of the process there. So we're changing the ion flux of sodium by the introduction of light, and changing that from cis to transretinal is what does that. Yeah, go ahead, Isabel.
Gray is going to be bleaching and going back for benefits cycle.
Just, yeah, cycling. Yeah, great. Thank you. Okay, so a couple differences here between rods and cones in terms of sensitivity to light. Okay, why are the rods more sensitive to light? It's because, here we go, because opsin just doesn't have as firm of a hold on retinal. Okay, so in low light situations, the retinal straightens out and it can get recycled and put back on. So this is how we see stuff at night, right? This is how we look up at the stars and we can see those stars. You notice you can never see a star clearly, partially because it's millions of miles away, also partially because we're just using our rods and we can't use our cones for that dim of light. But under real bright light situations, the retinal can't reattach, and we don't really go through that cycling process. And so we're not really using our rods when we're in bright light. Okay, and this is kind of the idea of like one of those flash bomb things that can be used as well, like in the military, they throw this bomb in, it just makes it super bright light. It can take up to 40 minutes to kind of reattach all the retinal in our eyes. And so when that happens, I can just kind of debilitate a group of people because they can't really see anything until all that recycling happens. So with cones, um, they're much less sensitive, and that's because the photopsin has just a stronger hold on the retinal. Okay, so in low light situations, it's below the threshold, and so we don't even use our cones, right? We're not getting any input from our cones in low light situations, so the retinal just stays attached. But in bright light situations, now the retinal can detach and reattach and go through that recycling process, so we can keep refreshing the image that we see. So if you're done filling that in, you can go ahead and go to the next slide. There's just a table there, kind of a little summary of what we talked about so far. You can start filling that in with your team. And then after that, there's a clicker question that I'll open up as well. So you can work on those things, and I'll leave this up for a sec so you can finish writing. Yeah, so you can work with your team on filling in this table and then answering that question on the next slide as well.
Not very. Also, those ones red, red. So for the. Yeah. And then. And then. Yeah, the rods don't like.
Gonna get out there for class? or what?
Already about out.
Did you this morning?
7:25.
Yeah,
I don't have class until right now, so I have to go like 10:30 to 12.
nice. Awesome. There's so many guys out every afternoon and
Because everyone works from home.
Yeah.
Or something.
some,
Like,
like, you guys have jobs, yeah. Yeah.
They just beat everyone out.
Yeah, I know.
But yeah, because I was like, I feel like even just like a couple of years ago, like I feel like it'd be empty more of these times.
Yeah, yeah.
Not at all.
I know, I know, I know.
Nice,
Yeah,
because they're like getting
That's
more
cool.
used to that, like that they're going through.
just there. Yeah, that's awesome.
Yeah.
Hear that allopsin and photopsin are resistant to that.
Yep.
Photopsin is a part of the cones, so and cones are less sensitive, so why is it?
Oh, just like they all absorb light in one way or another.
Yep.
But there's still a difference in sensitivity, but they do all absorb light.
Okay,
Yeah.
sounds good. Thank you.
Mhm.
And then rods there. Oh, yeah. Or no, rods are in like, it's just really or otherwise, smaller. Color vision.
Like, I feel like you just can't. Yeah.
All right, then once you're done with the filling in that table, you can go ahead and work on this question here.
I think it is like for, but for like that homes, like they're more perfect homes. That's the thing with the bright light and everything. Yeah. So like more sensitive. That's what I'm just trying to remember. Yeah. At least that's where I put it across the top. Yeah.
All right, so go ahead and plug in all those answers. Make sure to hit the send button with this type of question because you can put in more than one.
Yeah. Yeah. Well, there's all better size, so any one.
All right, so just everybody go ahead and put some answers in here. Go ahead and just hit that send button on your clickers too. I want to make sure everybody's answers get in.
You sign. Next game. And then. Wait, bronze.
There's still about 10 or so more of you that just probably need to hit the send button just to make sure. So go ahead, hit the send button. There we go. We're close. Maybe still about 4 of you still. Yeah, I think we're pretty close. All right, so most of you said A, D, and E. So that's what most people said. So on A, there are 100 rods connecting to one bipolar cell, whereas typically only 1 to 3 cones. Okay, that one's right. And then most of you said D and E as well. So D, rods are more sensitive to light. Okay. And then E, if the brain gets a signal from one cone via one ganglion cell, it knows exactly which part of the retina that cone is found in. Yeah.
Bro, it's talking about like sensitive. Is it saying like what, in what way is it sensitive?
It means like the amount of light that it takes to stimulate it. So if it's something, if it's real sensitive, then it would be a low amount of light. If it's not very sensitive, then it would be a lot of light that it takes to stimulate it.
Okay.
Yeah. Good question. Yeah, Ethan.
Like, cause them to be less precise.
Yeah, it's not it's not really related to that. Actually, I was thinking that too as I was reading the question. It's not really a direct connection. It's true, but it's not really directly connected to this question. So I probably need to rephrase that. But yeah, good call. Good. See, questions show that you're understanding things right there. Okay. Okay, let's go back to the table here. All right, we'll work through this briefly here. So rods are not color vision. Cones, yes. Okay. This is just all about the type of protein, right? So it's opsin versus photopsin. Okay, sensitivity to light would be high and low, right? This has to do with how hard or how well the retinal is bound. So retinal binding. Okay, resolution. This is high resolution, or sorry, there we go. Low resolution, high resolution. This has to do with that question we were just talking about, right? The ratio of rods to ganglion versus cones to ganglion, right? That's the key part. So wiring, we'll say. And then visual field size is kind of like an idea of like how much of the image that you're seeing is going to be kind of controlled by a single rod or a single cone. And so with cones, it's considered a small visual field, and with rods, it's a large visual field. And this also has to do with that wiring that we were talking about as well. Which one? Under what?
Yeah, like
Binding, retinal binding. Yeah. Opsin and photopsin. Yeah.
thank you.
Yeah.
Okay. Mine is- Your phones are-
Yeah, good question. So the question was, with color blindness, what's going on? There's a couple different things. A lot of times it's just actually missing one of the cones completely. So it's a genetic um, uh, deletion type thing where you're just missing the gene for a certain color of photopsin. So then it's just not produced. And then it can also just be like a malformation of it as well, where it's just not quite as functioning normally. But usually it's just kind of missing one of those types of cones completely. Yeah. Okay. All right. Well, let's dive into a little bit about how we see and how the eye responds to images. Okay. So when we look at an object, we're actually seeing light that's reflected off of the object. That's the key part, right? Where most objects don't emit light, right? So we're not seeing light that an object is sending out itself. We're seeing the light that came from something else and bounced off of that object and then went into our eye, right? And so if there's a certain object that reflects all the light, then that's going to look white to us, right? Because that reflects all different wavelengths of light. Okay, if there's an object that absorbs all wavelengths of light, then that looks black because none of the light comes back to us. Okay, so that's one thing to remember. The second thing is when light bounces off in an object, it bounces off in every possible direction and every possible angle. Okay, so when we have something really close to us, we get a lot of light rays into our eye that are very divergent, meaning that they're all going out at super sharp angles. Okay, so close object, we get lots of divergent light rays hitting our eye. If it's a far away object, then the light that bounced off of that red car Tesla over there and came to my eye, only the light that was going super parallel to start with is going to hit my eye, right? Everything else is going to miss my eye, right? So I'm only going to receive really parallel light beams from that car way over there. Okay, and light is packets of energy, photons traveling in those waves of higher and lower energy. Okay, so let's talk about this difference between near and far objects. Okay, so when we have something like an apple, that's all this light is bouncing off of it, going towards our eye. Okay, that little shaded blue circle in the middle is supposed to kind of represent our pupil and our lens in this example. Okay, so when an object is really close to us, we actually want to try to miss some of the light. First of all, because there's a lot of light bouncing off of that object, making it to our eye, so it's more than we need. And second of all, the really sharply bent rays way out here, that's going to be too hard for our eye to focus those, right? So we shrink our pupil down with a close object, okay? So we constrict the pupil, okay? And then secondly, since we are getting a lot of light into our eye that is really sharply bent, it's going to take our lens. We need a stronger lens to focus that light than we would if the light's coming in really straight. Right? So we're going to have a more convex lens. Okay, so with a far object, we don't get much light that actually hits our eye. So we're going to dilate the pupil. Right? And then we are going to flatten out the lens or make it less convex. Because the light that's coming to us is already going super parallel, so we don't need a lot of focal power to bend that light very much. Yeah, go ahead, Ava. Yeah. Yeah, wider is the way to think about it. We typically say more convex, but it's kind of like the lens is like a double convex shape like this. And so when we flatten it out, it kind of does this. We make it more convex, it kind of does that. Yeah. Mhm. Okay. All right. So a couple other things that happens to the light when it passes through a lens, any convex lens, as light passes through it, it gets refracted, right, which is just being bent. But when it refracts it, it also flips it upside down, but not only upside down, it also reverses it left to right. So it's kind of a weird thing to think about. But if you look at this little image, it kind of helps. See, this orange one was kind of in the back top one, and then it went through, and now it's on the front bottom one, right? So it not only flipped it upside down, but it also flipped it this way too, right? And that's just what happens, okay? But there's pretty much three convex lenses that the light passes through in our eye before it hits our retina. So that means it ending up upside down on our retina. And so then it's our brain's job to flip it over for us to see it. And so there are certain types of glasses that you can wear that just have a single convex lens that makes the image show up right side up on your retina, but then your brain still flips it over, and then you see the world upside down while you're wearing those glasses until your brain adjusts to that, and then it flips it over again. So yeah, it's pretty crazy. But yeah, so our cornea is a single convex lens and our lens is a double convex lens. So it always has to be an odd number of lenses that it goes through. And so that's built into contacts and glasses as well. But yeah, so that's just kind of that. And again, the more convex, the thicker the lens is, the more it can converge the light, it can bend it. And the less convex it is, the less it converges, the less bending of the light it does. Okay, so we've got three things that happen in our eyes, kind of these three reflexive things that happen when we look at something and it looks blurry. That stimulates three reflexes for us. Okay, so it's going to be a change in the lens, so accommodation of the lens. It's going to be if we're talking about an object coming closer to us, it's going to be constricting our pupils, and then it's going to be moving our eyeballs inwards to look at that thing as it comes in as well. Okay, so it's combination of the lens, changes the size of the pupil, and movement of the eyeballs. Let's just watch this quick little video. It's pretty funny. Use a rubber ducky to demonstrate this, but it's short and it does it well. So let's see if it works on my iPad. Yeah, the iPad never does great for this. Don't know why. It's actually working now. Okay. Hold on one sec. Almost got it. There we go. The sound is always the second part that never works. Ay, ay, ay. It's probably not even worth all this trouble, this video, but I'm doing it anyways. Okay, let's try it one more time. The sound is always a pain. Here we go. Nope.
Using this example.
There we go.
Ratings such as sudden movement that takes place during convergence can be seen. Convergence of the eyes keeps the image of the object of interest centered on the fovea, part of the retina where resolution is highest. If the eyes do not converge appropriately, diplopia or double vision occurs. Second, the pupil must constrict to restrict the entry of light rays diverging from a near object, since diverging rays cannot be bent enough by the periphery of the lens to make them fall on the fovea. If the pupil were to remain dilated, the image would be blurred. Finally, the shape of the lens must change, increasing its refractive index so that the light rays passing through it converge on the fovea. In distance vision, the lens is pulled at its equator by the suspensory ligament so that it is relatively thin. When the muscles of the ciliary body contract, the tension on the suspensory ligament decreases, and this allows the lens to assume a rounder shape, increasing its power to bend light. As a result, the image is focused on the fovea. Combined convergence. Pupillary constriction, and rounding up of the lens all function to keep an object in focus as it approaches the eye.
Okay, so yeah, it's just kind of a nice visual to show what's going on there. And so we'll walk through a couple examples here next. And still lost the Apple TV. Hold on one sec. Okay. Yeah, so we'll kind of put all that together here in a sec, but first of all, let's talk about the lens. Number one, the lens size or the lens shape is controlled by these the ciliary muscles, okay? And those are out here, right? And then those ciliary muscles are attached to ligaments called the suspensory ligaments, and then those ligaments are what's attached to the lens, okay? So when a circular muscle like this contracts, it gets closer to the lens, Okay. And so that allows the lens to become more convex. When it relaxes, it pulls away and it allows the lens to become less convex. Okay, so the way that the suspensory ligaments are working here, when when the ciliary muscle contract, then that is going to, again, make the muscle get closer to the lens. So that loosens up the ligaments and just lets the elasticity of the lens itself make it become more convex. So that loosens the ligaments, which allows it to be elastically just bounce back and become more convex. And then when the muscle relaxes, it pulls away from the lens, tightens up these ligaments, and then that is what's going to flatten out the lens and make it less convex. It's going to pull it flat. Okay, so if we just let the lens be by itself, it's going to be as convex as possible. It's only when we pull on it that it flattens out. Okay. All right, so let's walk through the steps that happen with focusing. Okay, so when we're trying to focus on something that is getting closer to us, or we look from far away to then all of a sudden something that's close to us, three things have to happen. Okay, first of all, with near vision, the light rays are, yeah, that's funny. That's the wrong word. I don't know why I changed that. That needs to be the light rays are more divergent. Okay, meaning that they're shooting out at strong angles or acute angles. Okay, and so then we need to bend the light a lot. Okay, so that's part of it. So with the lens, we use our third cranial nerve to contract those ciliary muscles, which then allows our lens to just elastically become more convex. So that's number one. Okay, so with all of these, you need to know the nerve, the action of the muscle, and then kind of the why, right? The why here is because the light that's coming in is really divergent, right? So we need a stronger lens to bend that and focus it on the retina. Okay, with the pupil, again, this is cranial nerve 3. Okay, we activate that to contract the pupillary sphincter muscle. It's going to shrink down the pupil and it's going to constrict it. And this blocks some of those really divergent rays of light. So we're only getting the more parallel light into our eye because some of the light rays are too strongly bent for our lens to have the power to focus, right? So that's the why there. And then the eyeballs themselves, they need to move medially so the light can stay on the fovea centralis, especially if that object is moving, right? Because it's bouncing off at different angles as it moves. So our eyeballs need to move as well to keep that focal point landing right where all of our cones are on the fovea centralis. All right, so we're going to use, again, cranial nerve 3 to contract those medial recti muscles and make our eyeballs converge. Okay, so let's walk through the other one. So with far vision, the light rays are going to be, let's see if I messed that one up too. I didn't. Okay. Light rays are going to be more parallel. Okay, because again, the light that actually makes it to my eye from way over there, it had to be parallel to make it that far. Otherwise, it's gonna miss either way, right? So we don't need to bend it very much. Okay, so the lens, the ciliary muscles relax, the lens flattens out, and it's becoming less convex. Okay, since there's not much light making it to our eye, our pupils need to dilate. We do that via less activation of cranial nerve 3, not via that pupillary dilator muscle. That was the one that the sympathetic nervous system controlled. This isn't a stressful situation. It's just looking at something far away, right? So we're going to deactivate that pupillary sphincter muscle, relax it, and that dilates the pupil. And then finally, our eyeballs can move out. They can diverge. This is via the lateral recti muscles, the ones that move our eyeballs out. Those are driven by the abducens nerve, cranial nerve 6. So with each of these three actions, with an object moving closer to you or an object moving further away, you would need to know what happens to the lens, what happens to the pupil, which way the eyeballs move, and you would need to know the muscles involved, the nerves involved, whether they're contracting or relaxing, and the why behind each. right? So the Y with the lens is always about how much we need to bend the light, right? The Y with the pupil is about how much light we want to receive or block, depending on if it's far away or close. And then the eyeballs moving is always all about keeping the light focused on the fovea centralis. Okay, questions on that? Okay, all right, so a couple of things with vision problems, okay? So the two most common vision problems that you've heard of will be farsightedness and nearsightedness, okay? So myopia is when we can't see far, and the typical cause for that is actually that our eyeball is just a little bit extra long, okay? And so when our eyeball's too long, that means that the focal point is in front of the retina, right? The place that we typically, that our eyes trying to focus is lands in front of the retina instead of landing on it. And that's why it's called nearsightedness, is because it's the focal point is too near, right? It's in front of the retina, okay? And so the way we correct this is we need a lens that's going to push that focal point back some, right? So we need a concave lens for this. We never have a concave lens in our eye, but we can put concave lenses in glasses and contacts, right? Hyperopia is the opposite. When we can't see near, and typically it's because of a short eyeball, so the focal point would land behind the retina if the light could get all the way through, right? So with this, we need a stronger, we need more focal power, right? So we need a convex lens to tighten up that focusing that happens. Okay, so those are the first two. And then astigmatism. How many people have some astigmatism? Yeah. Yeah. The tricky part about astigmatism is it's very specific to a certain location on your cornea. And so it's typically an irregular part of your cornea, can be the lens, but it's mostly the cornea. And so, for example, like right here, there's a little bit of an irregularity in your cornea. So when the light passes through, it kind of scatters it through that spot. And it ends up resulting in multiple focal points like this one up here on your retina. And so the way that they fix that is they put a little cylindrically shaped lens in part of your lens, right in that spot where the astigmatism is. And so if you have astigmatism and you take your glasses and you flip them upside down, they don't work anymore, right? Because that little thing's not in the right spot. Same thing with contact lenses. With the contact lens, for astigmatism, that little cylindrical part has to be right in the right spot. So when you first put them in, how many people have contact lenses and have astigmatism? When you first put them in, it's kind of blurry, right? It's because there's a little weight in the bottom of that lens that makes it eventually settle in the right spot, but it takes a second to do that, right? And you can't really tell what the right spot is. And it's all because of that defect is a specific location on your eye. So yeah, so we can, oh, and then the last one here is called presbyopia. Presbyopia happens in all people when they age, and that's when your lens loses its elasticity. And so even though we can tighten up, we can loosen up those suspensory ligaments and let our lens become more convex, if it doesn't have the elasticity to keep becoming convex like it used to, then we just won't have as much focal power in our eyes anymore. And that's why your near point of vision moves further and further out as you age. My grandpa's got the newspaper way out here, or the phone probably now, but yeah. So yeah, and so these kind of show the different lenses, right? So we see a convex lens being used there. All right, so that would be the correction for that one. We see a concave lens being used there, so that would be the correction for that one. And then we can see this is astigmatism here. Okay. Questions on that? Okay, so this last concept is we went through all of it last semester, so it's nothing new, but it is important to remind yourself of this and make sure you know it for sure this time if you didn't quite get it the first time. It's this idea that the medial sides of our retina connect to axons of those ganglion cells that are going to pass to the other side of the brain. Okay, so the medial side crosses through this optic chiasm on both sides. Okay, but the temporal side, the lateral side, stays on the same side. Temporal side stays on the same side. Okay, So the way this comes into play has to do with visual field. So our right visual field will be over here. Everything that's coming into my eyes like this, into my right eye, most of that information is going to hit the medial side of my right eye. Oops. And then in my right visual field, sorry, most of that is going to hit the lateral side of my left eye because light can't come in and like make a U-turn, right? It's gonna go straight in, right? Yeah. So the lateral side from here, it's going to stay over here. The medial information from the right eye is going to cross over and end up over here, right? So our right visual field is processed by the left side of our brain, whereas our left visual field is processed by the right side of the brain. Okay, so if we have, and then this plays into damage to these areas, right? So if we have damage right here in the middle, because we have a pituitary tumor, it pushes on that optic chiasm. What's our visual impairment that we have? As remember from last semester? If we got pressure right here in this middle point here, what does that do to our vision? Can't see the outsides, right? We lose peripheral vision because peripheral vision hits the medial sides of our retina, right? And both the medial sides of our retina have to cross through here, right? So we get tunnel vision when we have a pituitary tumor because it pushes right there, okay? Yeah, so you'll need to kind of be able to work through those similar problems. This is just kind of for your practice here. You can kind of fill this in and yeah, just practice, okay? So all right, guys, real quick, hold on one sec. Let me tell you one thing about the honor lock situation. Just a couple tips on that. Number one, you really cannot talk out your questions, okay? Because you know why? Because you can talk into Chat GPT and then you can just see it all coming up on your iPad, okay? And honor lock flags that. So every time you're talking, honor lock will flag that, okay? So you can't be talking the questions out loud, okay? Secondly, try to aim your camera down a little bit, like just the top of your head is fine. I'm more interested in what you're doing with your hands than I am what you're doing with your chin. Okay, so those are the two things. Okay, can't be talking. And when you do the room scan, just show me. Here's my iPad. I'm using it to do to pull up my notes or whatever. That's fine. Okay. All right, guys. Have a good weekend. We'll see you back on Wednesday.
It's fine if like other people are in the room, like.
Yeah.
My roommate.
Yeah. It might flag it if they're talking, but I
Okay.
can always see what it is that it's
Try
not
to
you
tell 'em.
talking. Yeah, it's okay. It's not a big deal. I can look at it. Yeah. Hey, Sydney. Yeah.
I wasn't sure if it was still there from last semester, but I saw one combination.
I just added it. I added it like right before class. So I got them all in there for this first one. Not for all of them yet, but I'll get them all in later. So yeah, good sure. You were talking. It's okay. It's all right. No, I would.
Oh, that was-
Yeah. No, it's totally okay.
That totally makes
Yeah.
sense.
Yeah, for sure. I didn't
That
think
was
you were
like-
doing that, but it just made me, it just triggered my memory to remind the class to not do that. So yeah. Okay. All right. Yeah. Yeah. Let's take a look.
But
You registered. Okay.
Okay.
See if it works.
I just gotta be back there for about, like, around. Sore. Gross. Be back at 5. I guess it's right there and doing the phone.
Okay. Yeah. Charlotte E, right? Yeah. Do you have your phone? Pull up the website. Just go to like, you can Google like iClicker, login.
Yeah.
And then once you get there, show me. It looks like you're in the class, but it looks like your Clicker ID is not connected to your name. Yeah. Yeah. Here.
Oh, yeah, I was wondering, for the time limit, the EC, I was wondering.
I added it, for the quiz. I just did this morning. Yeah.
Thank you.
Yeah. you're right. Hey.
So, because my participation didn't go through on Wednesday, I was just
Yeah.
wondering if it went through this time.
Yeah, let's see. Oh, it's because I probably was that close to that. Yeah, you're good.
Okay,
Yep.
and then last question. So for the notes that are on the iPad, do you want us to like tilt our computer where it shows the notes on the iPad?
Just at least in the beginning when you're doing the room scan, so.
Okay, so you could like flip it over and then like put it back on us basically. Okay, sounds good. All right, thank you.
Yeah. Thanks.
So for the exam or for the quizzes,
Uh-huh.
is Command F okay when it comes to like our notes? Because on my good notes, I can
Mhm.
Command F and like look up.
You're doing it on a separate device though, right?
Mhm.
Yeah, it won't catch that, yeah, but yeah, you can do that, yeah.
It's me typing, so I don't want it to look like I'm like.
Oh, because you have like your computer you're taking the test on,
And
and
then
then you have like a keyboard with the iPad or
No, it's just like typing on the screen.
typing on the screen, yeah, that's okay, yeah.
I see. Thank you.
Yeah.
Is my, I don't know if my participation points went in.
Look,
Also, for the reading quiz,
Yeah.
was like my clicker not working?
um,
I don't, there might have like,
yeah, I do have your score.
Okay,
Did you
'cause-
see the score in there?
yeah, cause like I thought so for that one, was it like a thing where you like, were you supposed to push the up button to like
To
do
go to the next one, yeah,
that make,
put them all into one,
yes,
do it, okay.
cause it did this and I was like, oh, okay, that means he's probably wanting to put it and I sent it all. So I was like, that's why I was so confused.
Let me see, I might be able to pull up what you sent.
Cause I was like, okay, send,
Mm.
or I put like something send. Like, so I was like,
Let me check something real quick. I could be able to pull up exactly what you said. Let's see. Somehow you got one, you got 8 point. Maybe you just put the first one in. Usually when you put them all in, they don't get any points.
oh, okay.
But somehow you got 1 point. Did you pull it up there, Charlie? So, okay, so this one. So go to. Look at the backwards. Did you put your, that one in there? That one matches what you have?
Yeah, I think this is. Cause I originally had my old one from last semester. Switched it to new.
Yeah, looks like the right number. So here's the other thing, go back. Yeah, it looks like your, okay, hold on. Oh, yeah, this one. There, you can see that, Jim. So this is the problem, is because, yeah. Did you get this just this semester from
Yeah,
Level Books?
yeah, I had to return, they made me return my old one.
So take this back to them right now and tell them that it doesn't have an active subscription. So when you buy a new one, it comes with the year-long use of it. But if you have a used one, then it doesn't, you have to pay separate for the registration. And so, they can either give you an access code that they pay for, or they'll just give you a different clipper. So when you do that, you'll have to put the new clipper number into your account, but don't delete the old one. So I can still see your scores.
Okay.
All right.
Thank you.
I think maybe like when I think I meant to, I think when I pressed like I guess letter E, I think that was like the only one that's sent in because I sent it and then I pressed the button again
Yeah,
and then for like each one. And so I think it only counted like the last one that I think.
yeah, I can see here what you just said. That's exactly right. This is what you said.
Oh.
So if you would have put them all in one, then I would have been able to like figure out what.
Oh.
I can't,
Okay.
So,
Oh my gosh.
it's just 5 points.
Yeah, I know.
Yeah, it's connected. You're good.
Okay.
Yeah.
Thank you.
Okay. Yeah. Hey, how's it going?
So
your name?
Trevor.
Trevor. Yeah.
Yeah.
Nice to meet you.
Nice to meet you too. I have a question. I think not sure.
Okay. Yeah, it's fine.
I want to go into acupuncture
Oh, okay.
and my advisor is Professor Anderson. If he
Yeah.
doesn't know quite as much about it. So
Yeah.
I don't know if you would have an idea of like what trajectory I should go on here if there's like a pathway.
Yeah.
Go down.
It's a good question. I'd say I haven't had too many students going that route, but the ones that I have kind of been more like a pre-med type,
That's like the